Welcome to Precalculus 1. This is Module 1, which contains Section 1.1, 1.2, and 1.5. The first section, Chapter 1.1, is broken up into two parts. The first part is the real numbers and rectangular coordinate system. We're going to talk about the sets of real numbers, which include the natural numbers, which are the numbers you learn when you start counting 1, 2, 3, and so on. You'll also hear of these numbers referred to as the counting numbers. The next set, if we add 0 to the set of natural numbers, then we get the whole numbers. So those are the set 0, 1, 2, 3, 4, and so on. When we add negatives to the whole numbers, then we get the set of integers. You have the positive whole numbers, which are 1, 2, 3, 4, 5. You have the negative whole numbers, negative 1, negative 2, negative 3, and you have 0. You also have the rational numbers. Now, rational numbers, the definition is the set of all P over Q, where P and Q are integers and Q does not equal 0. What that means is it's the set of all numbers that can be written as a fraction. This P over Q is any fraction. The top number has to be an integer, the bottom number has to be an integer, and the denominator cannot be 0. If you have decimal form, the decimal representations of rational numbers either repeat or terminate. For example, if you have the fraction 1/3, 1 is an integer, 3 is an integer, so you know it's a rational number. Or if you write it as a decimal, it's 0.33333333, which is 0.3 bar. Therefore, it repeats. Whereas if you had the fraction 1/4, same thing, it's a fraction, 1 is an integer, 4 is an integer, or if you write it as a decimal, we get 0.25, which terminates. The next set of real numbers are the irrational numbers. Irrationals are any number whose decimal representation never repeats and never terminates. Now, can you think of a decimal number that never ends and never repeats? A couple of examples are 0.0100100001 and so forth. No part of that ever repeats and it never ends. We can just continue that pattern all the way out. Another type would be what I call the ugly square roots. Square root of 5, that means what number times itself would give us 5? Well, 2 squared is 4, 3 squared is 9, so the square root of 5 would be somewhere between 2 and 3. The fourth root of 71, can you think of a number that times itself 4 times would give you 71? Probably not right offhand. Now, pi is written as pi is 3.1415 ... and pi continues out forever and ever. It never ends, it never repeats, there's no pattern. So pi is one of our good examples of irrational numbers. Same thing with e. These are just constants that never end, never repeat, so those are called irrational numbers. Now, real numbers, that's the largest set. The real numbers are made up of the union of rational numbers and irrational numbers. So what we've got is like if this is the set of all real numbers, every real number is either rational or it is irrational. Okay, a number cannot be both. If it ends or repeats, it's rational. If it never ends, never repeats, it's irrational. If it's irrational, then we just call it irrational and we stop. Whereas if it's rational, we could go through and say, well, you know, if it's rational, it could be an integer. -4, -1, 1, 3, those could all be written as a fraction. -4 could be -4 over 1. 10 could be 10 over 1. Whereas other rationals are like 1/2 and 2/3. Those are not integers, those are just fractions, so they're sort of out there by themselves. In terms of integers, we could have positive whole numbers or we could have negative whole numbers. Okay, but when we talk about just whole numbers, then we're talking about the positive whole numbers. Okay, and then if a number is whole number, it could be a natural number. Now remember, the only difference between a whole number and a natural number is 0. So for instance, the way this works is if you have a number like 2, 2 is a natural number, therefore it is also a whole number, therefore it's also an integer, it's also a rational, and it's also a real. Whereas if you had a number like -5, -5 is not a natural number, it's not one that we count with, it's not a whole number, it's an integer, so that would be an integer, a rational, and a real. Whereas if we had a fraction like 3/5, it's not natural, it's not a whole, it's not an integer, it's a rational, which means it's a rational and it's a real. Or if we had some ugly one like the square root of 2, it's none of those, so it's not rational, therefore it is irrational. Okay, so here's a set of numbers. Look at the numbers and determine which numbers in the list are natural numbers. Now remember, natural numbers are numbers that we count with. 1, 2, 3, and so forth. So we've got -27 is not because it's negative. There's a decimal. 0 is not natural. Fractions are not natural. So we've got 4, 5.12, that's a decimal, that's not. 65 is natural. Square root of 40 is not. And 72 is. Now let me go back on this square root for a second. If it would have been square root of 4, then we say, well, you know what? The square root of 4 is 2. Then it becomes natural and whole and integers and all that. So just be careful. Don't just look at it and say, oh, there's a square root, so therefore it's irrational. If it's a nice square root, then it could be all these other numbers. Same list. Which of the numbers are whole numbers? Well, the only difference in naturals and wholes is the number 0, because 0 is included in the list. We know it's 0, 4, 65, and 72. Now we're to the integers. The difference between integers and whole numbers are now we have to include the negatives of any whole numbers. So now looking at that list, the only one that's a negative and a whole number would be -27. So our list becomes -27, 0, 4, 65, and 72. Remember our little tree diagram we did earlier? All of these numbers are also under the rational side. So we're going to have these 5 plus any that are written as a fraction or any of them that are written as a decimal number that ends or repeats. So we've got 0.66666, that one repeats. -9/5, that is a fraction of integers. That one doesn't end and doesn't repeat. And then we've already got the others. So our rational numbers are the integers that we had along with the repeating decimals and fractions. Now, what about irrational numbers? Irrationals are the decimal numbers that never end, never repeat, which usually consist of any pi numbers or ugly square roots. So going through our list, no, 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 no. There's an ugly one that never ends and never repeats. There's a square root that's not a perfect square. So our irrational numbers are 5.121221222 and so forth, and the square root of 40. Now remember, the real numbers are made up of all the rationals and all the reals. All the rationals and all of the irrationals. So our real numbers are going to be all the numbers in the list. Now, looking aside, if all of these are real numbers, what do we mean when we say not a real number? Well, real numbers are any number you can put on a number line, or any number that you can show on a calculator. Okay, so that leaves it wide open for all kinds of numbers. What would not be a real number? Well, there's two major types that we're going to address. One of them is anything over 0. When you try to do 5 divided by 0 in your calculator, you get an error message. That means it's not a real number. The other type is square root of a negative number. If you have the square root of -4, that means what number times itself will give you a -4? Well, any positive times itself is going to be positive. Any negative times itself is going to be positive. Therefore, if you're trying to take the square root of a negative, there's nothing that's going to work. And the symbol for that, sometimes we use is this little no solution symbol, or we'll just say it's not a real number. Now remember, we said a real number line contains all the real numbers. There is a one-to-one correspondence between the real numbers and the points on the real number line. Now what that means is every real number corresponds to one point on the number line. So if you pick any real number, let's say we pick 2, 2 would show up right here. People say, pi, what about pi? Where would pi go on the number line? Well, pi is 3.1415, so it's going to be somewhere right between 3 and 4, a little bit beyond the 3. Okay? The one-to-one correspondence also means that every point on the number line corresponds to a real number. So if I pick this point right here on the number line, then I should be able to go through and pull off the real number that it corresponds to. If we have our number line, the location, the number part on the number line, the location it is what we call the coordinate of the point. Okay, the correspondence is called a coordinate system. So this is the coordinate, this has coordinate of 2. This point right here would have a coordinate of -3. This right here would have a coordinate of 0.5 or 1/2. When we graph with 2 variables, or when we start graphing equations, we're not going to use the number line to show the real numbers. We're going to use the Cartesian coordinate system. And sometimes you'll hear it referred to as the rectangular coordinate system. And what this system does is, instead of having a number line, we have an XY plane, or the coordinate plane. And it consists of the x-axis, which the x-axis is this horizontal line that works just like a number line does. You've got 0 in the middle, you've got 1, 2, 3, all of your positives are to the right. You've got -1, -2, all of your negatives are back to the left. So that is what we refer to as the x-axis. We also have the y-axis. Now the y-axis is this vertical line going up and down. Same thing, 0's in the middle. Your positives go up, just sort of like a ladder would. Your negatives go down. I don't know if you can see these little negatives in there, but there's -1, -2, -3. Just like if you were going down in a hole, the further you go, the bigger the negatives get. Okay? the point in the middle where those two axes cross is called the origin. And we say that that origin occurs where x is equal to 0 and y is equal to 0. Now, the shortcut notation for that is, let's just write it as 0, 0. Okay, this is what we refer to as an ordered pair. Ordered meaning the order matters. It matters which one goes first. The x always has to go first. The y always has to go second. The pair meaning there's two numbers. We put them in parentheses. We separate them with a comma. Now, when we have our coordinate system, for any point, you have to give the x value location and the y value location. For instance, this ordered pair is 2 high. It's 2 off of the x-axis, which means that the y value is 2. The point is also 3 places along the horizontal line, so that means the x value is -3. So we call that the ordered pair -3, 2. Now, would it matter? What if we did the ordered pair 2, -3? Where would that one be? Well, that means that the x value is 2, so we go over to where x is 2. Okay, whoops, sorry, don't mean to put a point there. Go over to where x is 2, then y is -3, so you go down here to where y is -3, so x is 2, y is -3. Is this ordered pair 2, -3? Okay, so it does make a difference which one comes first. So just remember, you always start counting at the origin. Do the x value left and right. Do the y value up and down. When you draw the x and y axes, that separates the graph into 4 corners. The first corner, the top right-hand corner, is called quadrant 1. This is the most popular corner. The x values are positive, the y values are positive. A lot of times when you see graphs in a newspaper, most of the graphs come from this quadrant 1. Okay, then it goes in a counterclockwise circle. The top left-hand one is quadrant 2. X's are negative, y's are positive. Going on around, the next one is quadrant 3. And in that one, the x values are negative and the y values are negative. And then the last one is quadrant 4. The x values are positive and the y values are negative. When we talk about a standard viewing window, especially when we start doing our calculator, we'll refer to the x-min, the x-max. The x-min is the minimum value of x shown on your number line. The x-max is the maximum value of x. The x-SCL, that is your x scale. That's the distance between your tick marks on the x-axis. Then we have the same thing for the y values. We have the y-min, which is the lowest value of y. The y-max, which is the maximum value of y. We have the y-scale, which is the distance between your tick marks on the y-axis. So for example, when we talk about standard viewing window, you'll see it denoted x-min, x-max, x-scale by y-min, y-max, y-scale. So for instance, if you see the scale listed like this right here, -10, 10, 1 by -10, 10, 1. What does that mean? Well, that means when you're looking at a graph, the graph starts back here at -10 on the x value. That's your x-min. The x-max is 10. Each little tick mark is 1, so that means there has to be 9 little tick marks. 4, 5, 6, 7, 8, 9. On both sides. 1, 2, 3, 4, 5, 6, 7, 8, 9. And same thing on your y's. The lowest y value is -10. The highest y value is 10. Y scale of 1 means 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 little tick marks here. 1, 2, 3, 4, 5, 6, 7, 8, 9 little tick marks here. Okay? Now, if we gave you something like that, negative 20, 25, by negative 10, 50, 10, what would that look like? Okay? Let's draw our little box here, because this is on your calculator. You're going to see a little screen. Okay? That means that your x values go from negative 20 to 20, and your y values go from negative 10 to 50. So I'm going to start it back here just because I know that this is going to be negative 20, this is going to be 20, and that's going to split that right down the middle. Now your y values, the lowest y value is negative 10, and the upper y value is 50. Now back here on your x's, negative 20 to 20 by 5, so there we've got 5, 10, 15, 20, negative 5, negative 10, negative 15. So there's very few little tick marks. But think about it, it'd be hard to cram in 40 little tick marks on that little short space. Over here on your y's, every tick mark is 10. So from negative 10 to 0, there's none. 10, 20, 30, 40, 50. So that standard window would look like that. On your calculator, your y equals is where you're going to do your graphs. Right now, I've got negative 10 to 10 to 1. So this is what we call a standard viewing window. Okay, that's what it would look like. If I had some weird window, the way I would get that, you can go to Window and go through here and manually adjust and say, well, you know what? Let's go back to that one we had a minute ago. Negative 20 to 20, x scale of 5. Negative 10 to 50, y scale of 10. Now when we graph that, that's what our little window looked like earlier. Now, if we want to go back to our negative 10 to 10, go to your zoom, go to number 6. You can either scroll down to number 6 and hit enter, or you could just say zoom 6, and that would give you your standard window. I'm going to cut off right here, and we'll continue part 2 in just a second.